Thank you, Ferry. I'm going to be talking about composite materials tonight. More specifically, I'm going to be talking about carbon fiber reinforced plastic composite materials. These materials are used extensively now. The example at the top, civil aircraft, the most recent aircraft from Airbus, the A350, it uses 53% of carbon fiber reinforced plastics in the airframe. Large wind turbines with extremely large blades have become totally reliant on carbon fiber composites. The Formula One industry has been at the leading edge of applying carbon composites for many years now. And the final image at the bottom here is the BMW i3 series. It's an electric car. It uses carbon fiber composite panels and a carbon fiber composite frame. And we're going to see more car manufacturers doing this as they push towards electric and hybrid technologies. Let me start, though, by saying what carbon fiber reinforced plastics are. And at a very simple level, they're just fibers, carbon fibers like this, inside a plastic matrix here. But this image gives you no idea of scale, of course, and I'm going to be using images like this throughout the talk, but I want to show you once, at least, the scale of what we're talking about. So this is a photograph taken with an optical microscope. The scale here is 20 micrometers. So that's 21 thousandths of a millimeter. So these fibers, in this case, are 5 micrometer diameter. And carbon fibers typically run in the range from about 4 micrometers up to 10 micrometers. So let me tell you a bit about the properties of the carbon fiber before I move on to talk about properties of the composite. And these figures are from a carbon fiber manufacturer's website. They're extremely strong. 10 times as strong as steel is the quote I've put up here. And the other important factor you should know about is that they're also very light, a quarter the density of steel. Okay. And at this point, you may be wondering, why do we need this plastic matrix? Well, let's have a look. What I'm showing here is a carbon fiber tow. This is a collection of continuous carbon fibers. And I've got it on the visualizer here on the right-hand screen in a second, the same fiber. So 12,000 fibers. And you can imagine that if I apply tension to this, it's very good, not a problem. But if I put it in compression or try and do anything with it, it's pretty hopeless as a structural material. So it might be good for a tether or a kite string, but anything else it's not going to work for. So that polymer matrix there is actually there to support the fibers and distribute the applied load on the component to the fibers so the fibers can work and use their impressive properties. Now, to show, of course, having said that, then what we should be looking at are the properties of the carbon fiber reinforced plastic composites. And we're going to do this first by considering stiffness, and we're going to do this test. This is a plate specimen sitting on 2 supports, 800 millimeters apart. I'm going to apply a load at the center of the plate, and of course it'll deflect like this. And the measure of the deflection there, the smaller the deflection, the stiffer the material. The specimen's got this geometry. Remember, we're supporting it at 800 millimeters. When the specimen's going to overhang, it's 1,000 millimeters long, 4 millimeters thick, and 265 millimeters wide. And I'm going to look at 2 materials. I'm going to take a medium strength aluminium alloy, 6082 T6 for my technical colleagues, and a carbon fiber composite. This is a fairly early generation carbon fiber composite. TS is the fiber type, carbon fiber type, and 914 is a type of plastic matrix material, an epoxy matrix material. There's something else I have to tell you about this specimen, though. All the fibers are in the longitudinal direction here. So if we were able to go and look very closely at the end of the specimen, you'd see all the fibres running parallel like this. So we're going to do the stiffness test, and I need to apply the load in the middle of this stiffness test. We're going to do it here, and let me just get the camera up here so you can see what we're about to do. It takes a few seconds for this to come up, but while that's coming up, I'd like to introduce Jingjing's son. She's going to apply the load to these beams for me. She kindly volunteered. She's a PhD student working with me. She's working on ductile composites, actually. Now, before Jingjing stands on this, she's very keen. What you can see here, the edge that looks white is actually the edge of the aluminium alloy plate specimen. Okay. And Jingjing's going to stand in the middle, and we're going to see how it deflects. Okay. And you'll see, sorry, go on, Jingjing. It's all right. Some people were worried. You can see that the yellow behind is indicating how far it's deflected. And Jingjing and I took a picture earlier, and there it is. And you can just compare them to make sure I'm not misleading you here. So Jingjing, let's move on and now look at the composite version. Yeah. Okay, so we'll swap these around. Remember, they're identical size. So here's the composite one. Go on, try that one, Jingjing. Okay, so again, you can see the deflected profile here. And of course, the deflection is a lot less than that aluminium alloy one. And let's just put up the photograph here. You can see it's about half. Yeah? So we've seen these deflections, and we can see the deflection for the composite one was half of the aluminium alloy. It means the composite is twice as stiff as that aluminium alloy one. So actually, to have the same stiffness as the aluminium alloy plate, we can do it with less carbon composite material, of course. And what we're going to do is do it with a narrow one. So now instead of 265, it's 138 millimeters wide. So here is that specimen, and we'll just prove it's the case. So just before you stand on it, Jingjing. Oop. There's the aluminium alloy one that Jingjing stood on before, and you can see the deflected profile. And now, Jingjing's been very careful, but she knows it won't break. But anyway, there we go. You can see it is the same deflection. Okay? So we can use less composite material for the same stiffness. Jingjing, you can jump off now. Okay? Thank you. Let me turn this light off. I'll just... It's all right. Now, what I was going to say was, I wanted to compare the masses. And if we look at this, that aluminium alloy plate, 2.9 kilograms. The composite one, the reduced width one with the same stiffness, 0.9 kilograms. Less than a third of the aluminium alloy one. So let's move on and talk about strength. And I'm sorry, Jingjing. This is my artistic impression of Jingjing here. You remember she stood on the aluminium alloy beam. My question really is, how many Jingjings is it going to take to cause this to start failing? Well, I'm not going to ask Jingjing and colleagues to do that for me, but let's have a look. It's going to take 1.5, just as well I didn't ask them to do it. 1.5 Jingjings will start this failing. So let's move this to one side and look to see what's going to happen with the composite one. Now this is the full width composite plate. Okay? So there's Jingjing standing in the middle, but she's going to have to move along to make room for a friend. And then they're both going to have to be fairly strong, because Jingjing's going to have to hold 3 people up, and her friend is going to have to hold another 2.5. So 7.5 jing-jings to break this composite one. Only 1.5 for the aluminium alloy one. And so now you can see these materials are very stiff, very strong, and very light. And therefore you can see why they're being adopted for weight-sensitive applications like that civil aircraft we looked at the start. But I'm going to tell you, it's not all good news, unfortunately. And we've got to go back and look at our description of the carbon fiber reinforced plastic matrix. Here it is, sitting here, carbon fibers and the plastic matrix. The bad news is that this plastic matrix has low stiffness, but more importantly, it's got low strength compared to those fibers. So if we're putting load on in the fiber direction, like those blue arrows, everything's fine. But if we put load in the transverse direction, we'll find we won't be able to put much on before it'll fail. So at this point, I'm sure some of my colleagues are thinking, well, he cheated in that comparison we showed earlier. There's that beam specimen again, and I'll show you why they probably think I cheated, because look at the end of the beam here. It's sitting here. There's the original undeflected shape, and here's the deflected shape. If you look in the lower half here, you can see of the deflected shape, there's the line of the end of the undeflected beam. You can see that in the lower half, it's been extended or stretched. And in the upper half, it's got shorter. In other words, it's been compressed. Okay? So why might they have said I cheated? Well, for the carbon composite one, of course, I put the fibers in absolutely the best direction to resist this extension and compression of the material. So the question is now, what would happen if we put the fibers transverse to the width of the beam like this? And I'm going to use this to illustrate how different the strengths are in the two directions. So there was Jingjing and her friends on the composite beam with the fibers running longitudinally. And here's the case with the transverse fibers. And there's Jingjing. But actually the bad news, Jingjing, is that we need half of you, I'm afraid. So it is much, much weaker. Yeah? And we've got to cope with it somehow, of course, in all these composite structures we saw earlier. So how do we cope with it? Well, think about this. Here's a piece of composite. It's got some load like this, and maybe some load in the other direction there, and so on. And it might have a complex pattern of loads on it. What we do is make a laminate. And the laminate has fibers running in various directions to ensure it can resist all those applied loads without transverse failure, transverse to the fiber failure. Of course, this is still set in the matrix. And the laminate, it's called a laminate because it consists of layers, of course. And I can show you the layers structure there. Okay. So this is the laminated configuration. And this gets over this in-plane weakness. But there's a problem with this. And it is that the only thing holding these strong, stiff layers together is the relatively weak plastic matrix. So each of those plies is connected to the next one only by the plastic matrix. And so it's susceptible to separation of the layers or delamination. If the loading's right, we could rip off that top layer, for example. Now, how important is separation of the layers? Well, we're going to have a look again at this stiffness test. And we're going to look at a different stiffness test now. And this is the reduced width. Sorry, let me have this. This is the reduced width beam again, carbon composite. But in this one, we've separated the plies over here every 0.5 millimeter. Remember I said this was 4 millimeters thick. Well, I've separated into 0.5 millimeter intervals. So now we've got 8 separate laminates there. And there, we can see this. And of course, because they're separated at each of these yellow boundaries, it means they can separate. Not only move apart, of course, but also slide relative to each other freely. So, let's have a look at this. So, there we go. And just before you stand on it, you will notice something already, and you'll have an inkling about what's going to happen, because you'll notice it's sagging significantly under its own self-weight. Okay, go on, stand on this. That was the one, careful, that was the one reduced width one without the separation, so it was the solid laminate. This one, well, look what's happened. When we have separation, Jingjing's actually standing on the floor here. The composite isn't doing anything. In fact, so there's a picture of it. In fact, the stiffness is less than 2% of the original plate. Okay? So we've lost a huge amount of stiffness. Jingjing, you can sit down. Thank you. So we've lost a huge amount of stiffness. And if we look at the ends of each of these plates, first of all, the intact one, well, there it is. Whoops, let me get rid of that one. There's the intact one. I'm just showing the profile of the end of the beam. It looks a little bit uneven, but it's to do with how it was cut exactly. But let's look at the other one, the one where the separations are. You can see every ply has slid relative to its adjacent neighbour. And it's because the layers can slide over each other, of course, that we have such a massive loss in stiffness there. So separation matters. How could the plies separate? Well, here's a laminate consisting only of 3 plies. And one of the things that can cause separation is impact. Impact's a great concern for aerospace applications, for example. So we get an impact on the plate, and potentially, if the impact's big enough, we'll get separation at the interfaces here. Here's another example. In this example, we've got the laminate again. It's supported by a T-stiffener here, bonded to the surface. And imagine we've got, say, pressure loading acting on there. Then it's again possible that we will cause failure of the interface between the plies, and we'll have separation of the plies again. And in these cases, I think the loading, it's fairly obvious why that loading's causing separation. But in certain situations, you can get delamination or separation of the plies, even if it looks as though the external loading wouldn't cause that effect. And here's an example, I hope. Here we go. This is a tension coupon, a composite tension coupon. The edge is being painted white, and it's being pulled apart. The video is running right now. What I want you to do is watch what's happening on the edge of the specimen around here initially. So there we go, something started to happen. And you can see it's gradually unzipping. It's actually unzipping right at the mid-thickness. Exactly the same things happening on the other side of the specimen. And this is just due to a tension applied longitudinally on that specimen. So, before we leave that one, let me explain why it happens. Imagine it's the laminates of this sort of layup. What I've got is 4 layers here. The outer layers have both longitudinal reinforcement, and the inner layers have reinforcement running horizontally. What I'm going to do is look at the front half of this laminate. So there it is. Now imagine in the test, we put an extension in the vertical direction like this. And I'm going to look at the plan view of the specimen, but before we go there, think about this. This front ply, with the fibers going vertically, when you extend it longitudinally, it wants to contract laterally. The rear one, with the fibers, stiff fibers running horizontally, contracts laterally as well, but very, very little. So the front one wants to contract a lot laterally, the rear one doesn't want to contract at all, and yet, of course, they're not free to just do that because they're bonded together. And so in plan view, that on its own, subjected to an axial strain, would deform like this. And then remember that this specimen actually comprises a symmetrical unit at the back here, exactly the same as the front one. And therefore, when we look at the plan view of this, we know the two halves are trying to do this. And it's exactly this problem here where the two halves are trying to curve apart, which starts pulling it apart at the edge. And what we have here during that test is that separation advancing towards the middle. And the material property that controls how that separation progresses inside the specimen is the separation resistance. And the test for doing that is shown here. This is an Instron test machine. It can apply tension loads to specimens. This will apply up to 50 kilonewtons. And we've got a specimen in here to measure this resistance to separation. Here's an enlarged view of it. The specimen's connected to the test machine at these points, and here it is. And all it is a composite specimen in which we've already separated the laminate at the midplane over a certain length. Then in the test machine pulls this machine pulls the laminate apart. The delamination or separation starts advancing along the midplane, and we monitor the applied force, the applied displacement, and the distance to the tip of the separation. So let me show you this, how we get this. So there's the original specimen before we start loading it. This is the force, this is the opening displacement, and initially it loads up nice and linearly. And we get to a point where the crack just starts to grow, and as soon as it starts to grow, the load starts dropping. And we carry on doing this test. We grow the crack. We've grown it to this position now. The load's dropped off a little bit, and the curve sweeps down like this. Now, of course, the work done by a force, constant force, is just force times distance moved in the direction of the force. If the force is varying like that, well, it's just the area under the force displacement curve. So this represents the work done, or the energy that's being put into the system to change the specimen from this to this, which contains a longer crack. Now, of course, in this state, it still contains energy because these arms are still bent. If we unload it, though, we'll get this much energy back out, and the specimen will be in this configuration. So the energy absorbed in growing the crack from this position to this one is just the area of the blue zone here, and I've called it U. Okay. So the crack's grown, of course, and the area that the separation front has swept through, I'm going to label it A, and then I'm going to tell you that this separation toughness, and it's often represented by this G1C here, is just the energy divided by that area. Okay. So for the material that we were looking at the start, this TS914 carbon fiber reinforced plastic, that toughness, G1C, is 120 joules per meter squared. So that's energy per unit area. But I should try and tell you how tough that is. And to do this, I'm not going to use a test machine. I'm going to ask for a volunteer to do the test for me. And let's see whether we need that 50 kilonewton test machine. 50 kilonewtons, by the way, is enough to pick up 3 average cars, I would say, maybe a little bit more. So, this is the specimen. There it is. I've just put 2 cords on here. And all I want is somebody to hold it at arm's length and pull it apart. I want somebody who doesn't look as though they've been to the gym a lot. That's important. I know you have. So, I need some brave volunteer here. Dan, are you going to do this for me? Sorry, I'm not suggesting you don't go to the gym, of course. You might.
Do I need my safety gloves?
No, no, no. Just hold it at arm's length. You can stand there. Yeah. Yeah. Oh, yes. Yeah, come down here and down. Yeah. Yeah. It's good.
Right, so just like that?
Yeah. Was that very hard then?
Oh, well, very, very hard, yeah.
He's lying. That was extremely easy, okay? We didn't need a machine that can lift 3 cars, okay? It takes only tens or maybe 100 or so newtons to grow that crack. And let me give you one other idea about how tough 120 joules per meter squared is. If you peel sellotape off a roll, that's only 100 joules per meter squared. So you've got an idea of how susceptible these materials really are to separation of the layers. So, maybe I've given you separation anxiety at this point, and you can see why it was in the title of the talk. But what I'm going to do is propose a cure for this. Okay? And it's going to take this form, and we're going to look at each one of these in turn briefly. So first of all, let me go and look at the materials one. And I ought to say before I do this, this susceptibility of these materials to separation is well understood by the designers, of course. And so the idea of having a structure which has a large crack in like that specimen and where load is applied normal to the crack, they would not do, clearly. The material I chose as well, I said it was an early generation carbon fiber composite. There are more advanced generations now which have larger toughnesses. So these ones are also carbon fiber reinforced plastics, but tougher plastics. So you can see we can get a system here which is almost twice, and the next one 3 times the toughness. And all of these matrices here are all epoxy-based matrices. If we make a switch to a different type of plastic matrix, we can get even bigger increases in toughness. So this one is a polyether ketone matrix, peak matrix, and it's got a toughness in the range of 2,000 joules per meter squared. So a big increase over that first generation material. So in difficult circumstances, the engineers can turn to much tougher materials. Now, it may be that they've only got a certain location they've got to worry about, and there are technologies available to deal with separation of the layers in small locations in the structure. And this involves putting reinforcement through the thickness. And there are various forms of this, and I'm just going to be talking about this type, which is called Z-pins. And they are actually cured carbon fiber reinforced polymers in the form of rods, which are inserted through the composite before it's cured, okay, or hardened. How does it work? Well, they're designed so that, imagine that fracture toughness test we did before. Well, this is a Z-pinned one, and they are designed so that these pins pull out as the crack's advancing. So the crack tip here, the separation tip advances, and in the wake of the tip, these pins are being pulled out, and in the process of pulling out, they're absorbing energy. And it's a bridge zone I've identified there where the energy absorption is taking place. If you rip the specimen totally apart, you can see you end up with all these pins sticking out of one of the arms. There's the pin, and I just want to say one thing about the toughness mechanism here. That's a nice round circular pin. But actually, the pins are not round. When we started doing pull-out tests on this, we found that actually they behaved rather differently from what we expected, and they absorbed considerably more energy than they would if they were simply round pins like this. What you'd normally expect to happen is the bond would fail, and then it would be resisted by friction as you pull it out of the hole in the composite. But actually, the pin is not circular, it does not have a circular cross-section, and actually it's twisted. So what we've done here is we've taken a real pin, and we've taken sections all the way down the pin and photographed them. Okay. And here is what you find when you play a sequence of those images. So the pin certainly is not circular, and it also twists as you go down. So imagine the pin being pulled out now. It debonds. Okay, there's friction there, but it's also got to deal with the mechanical interference of the pin with the hole as it's being drawn out. Energy absorption mechanisms. And how do they fit on this plot here? Well, it turns out Z-pinning can hugely change the separation toughness. And we're talking about ranging from a few thousand up to tens of thousands. And it simply depends on the length of the pin, so the pull-out length, and how many pins you put in a given area. So we've got ways of improving the toughness of the material. So now I want to move on to this inspection aspect. And of course the worry here is we might have a composite with a separation inside there at some position within the thickness. And how would we know from the outside? It's pretty tricky, isn't it? Because look at this material. It's black. You're not going to see anything from the outside. The commonest inspection technique, most effective, is ultrasound. And the technique goes like this. We inject an ultrasound wave into the panel from one surface. It hits the bottom, and it reflects back up. And if we did it over a separation here, what you find is the bulk of the signals also reflected back up from that separation. So imagine what we do then. We record the time of the signal to be transmitted from the top surface and received back at the top surface, and knowing the speed of sound in the material, we then know the depth to the reflecting surface. And clearly if that reflecting surface is less than the overall thickness of the laminate, we know we've got some problem inside our laminate. Now this is a laminate that I impacted. Actually, I just hit it with a hammer. And I don't know whether you can make out a very little light grey area there, but let me show you the zoom here. You might just be able to make this out, and you have to hold this to the light quite carefully to see it. Okay? And there's a millimeter scale. Well, maybe that's 2 or 3 millimeters across. And actually, if I flip the panel over, you would see a raised area on the back and maybe a split as well. But this is the problem with composites, of course. Imagine the fuselage you can hit on the outside. It may not show on the outside, but there may be significant damage inside. And normally you don't have ready access to the inside to check that. So there are various pieces of equipment for using ultrasound. This is a very recent one we've purchased. It's called a Dolphicam. Here's our panel. Here's the Dolphicam. It's got a square sensor there, which consists of a whole array of transducers which send out ultrasonic signals. It's a square sensor of 30 by 30 millimeters, and it can take an instant picture of what's happening in that zone. We've got a couplant, a gel couplant on the surface. All that happens is, the operator holds it on there, presses a button at the top, and captures an image on the laptop. And what did it show for this plate? Well, this is before the impact. We've got a depth scale here running from 0 up to 2.4 millimeters. It's nearly all in the blue region here, showing it's about 2 millimeters thick, which is good because that is the thickness of this plate. And then after the impact, quite a change. You see we've got a sizable orange zone here now, and it's at a depth of about 0.8 millimeters, just before the mid-surface. And from the size here, it's about 20 millimeters across this. So these are the disposal to inspect the structure. But there are other things on the horizon, and I'll just give a plug for this project here, because we've just been successful. We were awarded this proposal by this activity by Clean Sky, which is focused on making greener aviation in Europe. And it's a project called Sherlock. It's led by my head of department, Professor Feriali Abadi, and Dr. Sharif Corday, wherever she's sitting over there. Yes. And it's all about structural health monitoring. And this is about having sensors either embedded in the composite or surface mounted on the inside of the structure, which can monitor the whole structure. And we can quickly locate damage. So in this particular case, this is a section from the fuselage. We're looking at a plan view on this. These are all the sensor locations, and they send out signals, look at all the responses, and in the event of damage, the idea is, of course, they will detect the location. And in this case, the impact damage was here in this circle here, and this is the prediction, so fairly close to locating where that damage is. And of course, then they can go in with the type of ultrasound equipment I talked about earlier to characterize the damage in detail. So this is on the horizon, and you'll probably hear about this in a few years' time. So finally, let me talk about analysis. I'm going to start, just give one example of simple formula, and I'm going to give this one. This is something that Glyn and I did quite a long while ago. This is looking at a circular plate, and it's got a circular mid-plane delamination in there. And we did this to have a look to see what force would cause that circular delamination to grow. And it turned out the formula looks like this. And this is going to be the only equation I'm going to show. Let me just tell you something about the terms in here. The E is the Young's modulus, and this nu is Poisson's ratio. It's to do with the stiffness of the material, and we've already been talking about material stiffness. The H is the plate thickness, and this G2C, well, we already talked about a G1C, remember, it was the separation toughness. Well, that separation toughness we talked about before was in this mode, where we were pulling the two parts apart in this opening mode. But this separation toughness is for a sliding mode that drives the separation. So, and the formula is interesting, of course, because you notice it doesn't have the size of that separation in it. Now let me show you what we were using it for. This is quite an old set of data that was from tests done at Imperial College. This is damage area produced during impact testing. And plotted across the bottom is the magnitude of the impact force, the maximum impact force during the impact. And the experimental data is all the discrete points you can see, first of all for 1 millimeter thick plates, and then 2, and then 4. And the data has an interesting characteristic for each of these. Initially, for low energies, you get no damage, and then suddenly you start seeing damage. So that's the case for 1 millimeter. For 2 millimeters again, no damage for a while, and then you reach a threshold and you start seeing damage. And finally here, no damage, and then suddenly, when the force gets large enough, we see damage. Well, this formula is actually the formula that gives us these red arrows, which picks up the initiation of the damage inside these plates due to impact. So if the engineer knows what impact he's worried about for his structure, he can calculate the magnitude of the force and then use this formula to tell him whether he's going to have separation or not within that laminate. And now I want to switch to the other end of the modeling. This is advanced modeling using finite element methods. The department has worked in finite element methods for many years, and in finite methods for failure of composites also for many years. Professor Glyn Davis and one of my other colleagues, Mr. Dennis Hitchens, did a lot of work in this codes so that they could predict damage growth. These have been refined and improved by other colleagues, so Professor Sylvester Pignot and Professor Lorenzo Iannucci have developed algorithms for accurately predicting the initiation and the propagation of damage in these composite structures. The idea in this project was, this is a curved stiffened panel from representative of a fuselage. So this is the outer surface, this is the inner surface, and here's some detail. Suppose the structure gets impacted repeatedly by hail strike, for example, what would be the resulting compression failure mode, or compression strength? And all of this was done in a large E program led by Airbus called Saristu. Well, here's the impact tower we were doing the impacts with in our lab. They were tested using a 250-ton compression machine that was designed and built by the Aeronautics department quite a few years ago, designed by a colleague, Peter Gasson. I think he's here tonight as well. And so doing this compression. And here's a high-speed camera image just to show the failure that develops. They were impacted here, and you can see the failure initiates from this zone and zips across the panel like this. So that's what happened experimentally. If we now do the comparison between the finite element modeling and the experiments, so first of all, just for the impact, well, this is the damage detected by the ultrasound technique, and this is the one predicted by our numerical model, so we've got good agreement there. And then if you look at the force time response during the impact, the blue one is the experimental result, the red one is our numerical prediction, so good agreement there. More importantly, the behavior in compression, the damage from another ultrasound technique is shown here, and this is from the finite element prediction, running away from where the impacts were. And here is the force displacement during, and the green elemental one is the numerical prediction. So extremely good agreement between these. So, for all these reasons, the availability of stronger materials or ways to reinforce the through-thickness direction, the inspection techniques and the range of analysis tools for accurately predicting the behavior, I hope you no longer have separation anxiety. What I now want to do is to talk about this laminated architecture. We've seen it's a weakness, but we've seen we can address it. But we can actually exploit this weakness. And this is the laminated architecture. And what I'm interested in is whether we can use that architecture to modify the behavior of our composite. And the first thing I want to talk about is ductility. And I'm looking around for something now which I can't see. Oh. This is the same aluminium alloy as we had the plate specimen that Jingjing stood on. And I think I mentioned this. So there we go. Look, this is a very large displacement. The thing distorts like this. Specimen do this. Well, if we go back to our bending test that Jingjing did, and remember the lower half was being stretched and the upper half compressed. If we cut some material out of the bottom part of the beam and took it away to the lab and did a tension test and looked at the force extension response, well, we would see it looked like this. And if we were only putting loads in here, we could load it and unload it and go back to the original shape. As soon as you get past this point where the material starts to yield, you're starting to lose stiffness, so it means for additional increments in force, you get larger and larger displacements. And if we unload it from part way along here before it finally comes apart, then we end up with a permanent displacement. And so this is called a ductile behavior. Well, I mean, if my aluminium bike gets clobbered while I'm in a shop, I can come out and see it's dented. If my composite bike gets hit, I'm not so sure. And yet maybe it's got some internal damage that might cause me problems later. So ductility is an attractive property. And, oh, I'm going to tell you something about the composite though, just before we go on. I want to say something about the tension behavior of the composite then. There was the one for the aluminium alloy. The tension behavior of the composite is just this. It just goes up, and then it breaks at that point. And any point before there, I could unload it, and it would go back to its original shape. Let me show you what would happen in a flexural test. I can't do it here. It's rather messy. You end up with bits all over the place. But this is done with a test machine. So here we go. It's just going to carry on. Keep your eye on it. This it runs up to the original shape. But if we get up to that failure load, it'll go bang and disappear, okay? So, it's a brittle behavior we have with composites. And I've already said, it's clearly, certainly for some applications, important. Well, together with Bristol University, Imperial College is in a large high-performance ductile composite technology. We work with Bristol University on this, and it's funded by Bristol. And the aim is to overcome this lack of ductility we've talked about there in carbon fiber plastics. And so we've seen and transform it to this one. And we're looking at various approaches, and I just want to show you one that's exploited the laminated architecture. So here's an edge view of a carbon fiber composite plate. And what I'm going to do is, in the manufacturing process, plant some separations at these positions here. Now imagine we come along and pull them apart. Okay? So we distort the laminate like this. I'm going to fill these two voids now with a crushable foam, and you might have an idea about what I'm going to do here now. I'm going to subject this to tension. If I've got the design right, as I subject this to tension, the skins would like to straighten, of course, they're waves. They'll put the core foam here into compression. The core will start crushing. It'll allow the skins to straighten, and so we may get a ductile behavior. This will be the final form, and the anticipated behavior is of this form. There's force against extension. There's the initial stiffness before we get failure of the core, and then the core starts crushing, the waves start straightening, and when the wave starts becoming quite straight, we're starting to get towards the stiffness, the high stiffness of our laminated composite material, of course, and finally it fails. Here's the experiments, and Dr. Soraya Pimenta was working with me on this. I think she's here tonight. She's now a lecturer in the mechanical engineering department. First of all, whoops, we'll go back on that in a minute. Yes, okay. Here's the stress against extension behavior, which has the characteristic we talked about. At the top, here's an experiment performed on one of these wavy sandwich panels with 3 of these cells. And you can see what happens. We get exactly the behavior we predicted. Each one of these is crushing simultaneously and finally goes bang, okay? And the good thing is here, we're getting strains up to 8.5% here. These are very large compared to the strain to failure of the carbon composite on its own, which typically fails in the range of about 1 to 2%. Okay? So you can see we can introduce ductility by exploiting that laminated architecture. Potential applications, we're quite interested in this for blast, because you can imagine the oil would drive the material past here, and then we get quite large strains in the material, and then a high reserve strength, actually, to try and arrest any further damage to the structure behind. And we've already had about the possibilities. Morphing. And I'd better say a little bit about what a morphing wing could be. The idea is that instead of having those control surfaces, for example, that deploy on the edge of the wing, you'll have seen them when you've been looking at the aircraft as you've been taking off or landing. The idea is to have just a single continuous structure for the wing. And instead of those control surfaces deploying, okay, and it can be more efficient. We won't have any gaps between the main wing and the surface, for example. And it can also be that the mechanism for driving can be much simpler and therefore less maintenance. So that's what we'd like to do. This is one we actually made in a research project with MBDA. So you can do this, but there's a conflict when you try and make any of these morphing structures in composites. We know these carbon fiber composites are strong and stiff, and they're strong and stiff for a reason, so that we can provide a light structure. And then, of course, we want to say, oh, we want to deform this, and we want to deform it quite a lot, actually. And that's bad news, of course, because we've already seen these materials can't stretch very much. Having faced that problem, then I started to think about this issue. Can we make a controllable stiffness material? And what do I mean by that? I simply mean a material where we can switch off and switch on the stiffness on demand. Now, we've already seen something that changes the stiffness. This was that carbon composite plate without any separations, the monolithic plate, separations of the plies. And this was the one where we had separations, where the plies or the layers were able to slide over each other. So we've already seen something that could work for us. And I went to that with that idea. Sorry, that's just reminding you, of course, it works because the plies slide over each other. I went with that idea. This is one of the advantages of Imperial College. I went to my neighbouring department, chemical engineering, where I have a colleague and friend, Professor Alexander Bismarck, and told him about this idea and how I wanted to do it. And he was able to help me identify the materials and processes to make this work. And we've done two things, and I'm only going to show you one of them. So how do we do it? Well, here's a composite material. It's got 3 individual layers. And what we do is insert at the junctions between the layers a thermoplastic interleaves. This is just another polymer film. And the property of this thermoplastic is that at a certain temperature it softens. So layers can slide relative to each other. So below the softening temperature, there's no sliding. Above the softening temperature, the layers can slide. So imagine we've got this laminate at room temperature and we apply a moment to it. Well, we saw before that at room temperature there's no sliding at the ends and it should have its full stiffness. But if we repeat this at a temperature above the softening temperature of the thermoplastic, then we'll get sliding like this, and we know that tells us the material is going to have low stiffness. So we've done this. We've made these composites. This is a test we've done, a bit like the test Jing did, but we did it in the lab in a test machine. And well, it just consists of composite layers interleaved by these polystyrene layers. In this case, the thermoplastic was a polystyrene. So this is the force displacement response. And we did 2 tests at room temperature here, and they're identical response. Then we did a test at an elevated temperature, actually at 120 centigrade, and there's the response. We've lost over 95% of the stiffness here. And now I'm going to tell you that actually we did the room temperature one first, temperature 1 first, then we did the elevated one and lost all the stiffness, and then we unloaded the specimen and did it at room temperature again, and that's there. We recover the stiffness totally. This is a view on the specimen in the large displacement state at the elevated temperature. And if we went and looked at the ends, we see that sliding behavior that we saw before in the test that Jing did for me. It's that shear deformation of the polystyrene that allows this to happen. But there's something else interesting about this material that we realized when we were testing it, and it's shown in this video. And just before we do this, a lot of the work we've done is taking this material and putting it in an environmental chamber. But of course, we're interested to know how we can actually heat these in practice. In this case, you will see we've got things connected to the end. They're actually electrical connections to the end of the specimen, so we can use the fibers as heating elements in their own right, resistive heating. So what we did, we've heated this specimen up, and we do the bending test. And you can see it deflecting, and actually deflecting hugely. You wouldn't get anywhere near this if it wasn't at this temperature. And then we cooled it down. And if we cool it down while it's held in place and then remove the load, it stays there. So it stays in its high stiffness state in the shape we pushed it into. If we then heat that up, and I hope it's going to go, it'll spring back to its original shape. Now here, It hasn't quite gone back, but remember this thing's extremely low stiffness, and the stiffness of the wire connections here actually stop it going back here. But when we cool it down, it's got its full stiffness again. So let me just show you some examples quickly of the sort of things we've been doing to look at this shape memory effect. Here's a 90-degree bend specimen we made with interleaved with those thermoplastic layers. And then we take it and rest it on this mold. We heat it to 120. We deform it to this U shape. We cool it down, and there's the U shape. And then we heat it, and it should return to its original shape, of course. And here's the test being done. It's already in the U shape. You can see it being heated up. Is that being heated now? Okay, thanks, Joseph. You can see it being heated up, and away it goes, and heads back to its original shape. Okay. I'll just advance this. We were interested in the idea of being able to make structural sections like this, but be able to package them in a much smaller volume and transport them out to site and then heat them up, for example. So perhaps we'd like a folded up version of this box and then heat it and deploy it. So what we did was take our interleaved angle section and reshape them either into a U shape or a flat like this, and bond them to conventional composites like this. And of course, we hoped that when we heat it, it'll return to this box section. And here's another example of that. This one's, well, they're both being speeded up, incidentally, I should have said. They were sped up by a factor of 3 or 4 here. And eventually, this one will return to its original shape, square. Now, when we presented this at the European Conference on Composite Materials last year in Spain, immediately after the presentation, somebody came up to Alexander Bismarck and said, was this computer graphics? This doesn't look real, okay? And at the risk of something going wrong here, we're going to repeat this demonstration live, at least for those little angle specimens. So, Joseph, let's have a go at this now. Can we just switch this light on? Oh, you switched the top one. Thank you. We need to switch over. Have we got this? Ah, there we go. And while those are going, because you're going to see them real time now, I'll just say a little about potential applications. Okay, I mentioned morphing aircraft wings. Clearly, incidentally, we are not going to switch the stiffness off in the entire wing, otherwise they'll be wrapped around the top of the fuselage and we'll be in serious trouble. But it is something we're looking at and how we might do it. We might be rippling in this change, for example. A more immediate thing that we can see working well for us is deployment mechanisms for satellites, for example. So there's one in a folded state and deploying like this. And these type of hinges that we're showing here, and you can see them moving now, are ideal for this. They're in a stiff state in the stored state, and then we know exactly where they're going to end up when we heat them up. And then they're in a stiff state then at the end as well. The other thing right down here is an interesting one. Active softening of cars. Actually, it was the bonnet of the car, which can cause quite a bit of damage to pedestrians. This is where they were looking at car sensors. You know, of course, many cars have got collision prevention systems now. So if they can see they're about to hit a pedestrian, the idea is that this is work done by a group of research organizations funded by Europe that took our idea, having seen what we were doing, and they're exploring this possibility. And the final thing I should point out is we've got a patent application on this with BAE Systems. So I think those things are moving. The thinner ones, incidentally, have moved fast. This one's much, much thicker. It will eventually go, but it'll take a long while. So at this point, I want to thank you, first of all, for your attention throughout this. Well, let me go back. I've got to thank all those people that helped me with the experimental things you've seen in the videos and in this live demonstration here. So first of all, I'll tell technicians, Roland Hutchins, Mark Grant, Gary Senior, Joseph Majesti, John Cole, Keith Wolstenholme, Franco Giamaria. Two of my postdoctoral research assistants, Spiros Saras and Omar Bakareza. And then finally, Bohao Zhang, and last but not least, of course, Jingjing, who did the experiments for me. So thank you. Of course, the work that goes behind this has been done by many PhD students and many postdoctoral assistants as well, who I thank, and I've worked with many colleagues, so I thank them all. I've been to many inaugural lectures like this, incidentally, and many people stand up and thank their family, of course, for all the support they've given. But support's a euphemism. Really, they're talking about forbearance or tolerance or patience. As we academics spend a lot of time working away on the next conference paper or the inaugural lecture, for example. So I do want to thank my family. I guess I've been an absent father and husband on quite a few occasions, and certainly in the last few weeks. So I want to thank my wife Jenny and my children, Michael, Claire and Stephen, who are dotted around a bit actually, yes, okay, for putting up with me. And finally, I grew up in a house where there was always a workshop, either in the garden or in the garage. Things were being made or repaired around us all the time. And it's still going on now, of course. My dad is here, and I think with that going on around us, it was inevitable that one of us was going to end up in engineering. So I want to thank my dad for that. Okay, I want to thank you for your attention. I hope I haven't given you separation anxiety. Thank you very much.